18th century is drawing to a close. America has renounced her British king for a newly gained independence. France is in the throes of revolution. Her starving peasants have risen against their oppressors. But perhaps the loudest noise in the ears of history comes from across the sea, England, where a revolution of quite another character is taking place. In a small factory at Soho, Birmingham, mechanical power is being made possible through the engineering genius of a pioneer, James Watt.
That is the reason, Mr. Watt, that my foreman suggested that I should investigate the possibilities of your engine.
I understand. In brief, then, your problem is to keep your mill in operation continuously and without interruption.
Precisely, Mr. Watt. And with my existing water wheel, work is at a standstill whenever there is a drought or a frost. I take it that your engine is not affected by climatic conditions.
That is so.
But is it capable of doing the work of my water wheel?
Absolutely. I have every confidence in it.
Splendid. Is it possible for me then to inspect this machinery?
With pleasure. The actual working of the engine will be demonstrated to you, if you will be so good as to follow me.
This is indeed most interesting, Mr. Watt. Has this engine been working for long?
It's been in operation for about 2 years. You notice that parallel motion?
Yes.
I'm more proud of that device than any invention I ever made.
Now, assuming that I shall install this engine, can I rely upon its energy to operate my mill in a satisfactory manner?
I can assure you, sir, that my engine will give you more power than you ever had at your disposal. Why, at 15 strokes a minute, it produces more than 10 horsepower.
Horsepower? And what, may I inquire, have horses to do with engines?
I appreciate your question. Permit me to explain the term.
James Watt estimated that horses exert a pull of 180 pounds each at 180 feet per minute. That is the horsepower we know today, 33,000 foot-pounds per minute. The 13 million cubic feet of water that pass down Niagara's vast cataract every minute represent nearly 6 million horsepower. A cricket ball driven to the height of Mount Everest in nearly 1/3 of a minute would expend 1 horsepower. A rowing 8 develops approximately 4 horsepower, half a horsepower each man, for a spell of 20 minutes, whereas the normal man's maintained output is only 1/8 of a horsepower. To travel rapidly with leisure, the modern man adds to his own power that of the motor car, which, being so familiar today, will serve to show how horsepower is created. We are witnessing the very birth of power. On the test beds, newly assembled engines, previously inert, miraculously spring to life. But before this dynamic quality becomes manifest, much careful workmanship is necessary. The engine begins as a rough casting on which 74 machining operations have to be performed. The first of these consists of milling the various faces. These milling operations ensure that the end covers, bearings, water branches, and numerous other components can be correctly fitted to the unit. 23 milling cutters make quick work of these preliminaries. As the cutters remove unwanted metal, the cylinder block becomes presentable. The cylinders are bored with a first rough cut on a 4-spindle machine in which the cutters are accurately piloted into the bores. Multi-spindle drills next come into play, first drilling the bottom facing of the casting with 24 drills all operating in unison. There are quite a number of drilling operations, and all must be made with equal precision. The 8-spindle machines that drill the valve ports and holes for valves and tappet guides are grouped for control by a single operator. These drills work together on a virtually one huge machine, with all its spindles feeding down until their cut is finished, when they automatically withdraw. But the most spectacular of these multi-spindle tools is that which simultaneously drills 53 holes in both ends, one side, on the top of the engine casting. The drills advance from 4 sides and complete the operation in under 2 minutes. Very similar is the subsequent tapping operation, except that the taps, having cut the thread in each hole, reverse their motion and screw their way out. After many more milling, drilling and boring operations, the top and bottom faces of the cylinder block are ground. Several blocks at a time are held on the magnetic bed of the surface grinder and travel under the large grinding wheel. This enables the final and most important machining operation of all to be of extreme accuracy. These cylinder head studs are rapidly fitted by means of an electrically driven tool. The last operation is to fine bore the cylinders with a diamond hard cutter, making over 400 revolutions for every inch it moves down the cylinder wall. It cuts to an accuracy of 1.5 ten-thousandths of an inch. This accuracy is verified by a pneumatic micrometer. Any variation detected by the air jet in the gauging plug being magnified up to 9,000 times in the reading given by the liquid column. 1 ten-thousandth of an inch error would show almost an inch of movement of the liquid. By these careful tests, consistent power output is assured. Next to the cylinder block, the most important component is the crankshaft, which converts the thrust of power into rotation. First the journals and then the crank pins of the rough forging are turned. Designed solely for this work, the lathes are of very heavy structure to ensure that crank pins and journals will be in correct relative location. The oil ways are drilled on a special machine controlled by hand and very rapid in action. The operator skillfully feeds the drills forward and then withdraws them, repeating the action until the passages are complete. crankshaft machining concludes with grinding to ensure uniformity of piston stroke and thereby balance of power. The smooth finish imparted by the grinding wheel minimizes internal friction. Lapping then provides a superlative finish, giving a mirror-like surface to the journals and crank pins. The finished crankshaft is scientifically balanced. While rotating on this delicate machine, the slightest vibration is recorded on the dials. The unbalance is determined by the extent to which counterweights must be moved to secure vibrationless running. All the rotating parts must be vibration-free, so the clutch assembly is similarly balanced and the unwanted metal removed by drilling. The flywheel is rendered perfect on a special machine using a sensitive spirit level and a counterweight, for the output of power must be smooth at all speeds. The initial thrust of energy is exerted on the pistons, which must be made to the same degree of accuracy as the cylinders in which they work. The aluminium piston castings are turned in a high-speed lathe with 3 separate cutters operating together. For the gudgeon pinhole, only diamond boring will give the precision required. Then follows the drilling of the oil drain holes, speedily performed. A diamond tool is again entrusted with the final sizing operation, giving a superb finish to the outer diameter. Lastly, a special anodizing process gives the piston an exceedingly hard surface which resists wear and retains the lubricant. Accuracy plus hardness plus lubrication equal long life. But the modern car engine incorporates many other components: valves, connecting rods, tappets, camshafts, and so on. The machining of the connecting rod forging begins with milling. Before the big end is split to form the cap, it is broached. The powerful cutter in this machine is impelled by hydraulic pressure. The final operation is to grind the big end so that the bearing shells fit perfectly and are in alignment with the gudgeon pin holes. Valves, which begin as a steel bar, are produced by an upsetting process, electrical energy and hydraulic pressure combining to create a mushroom of glowing metal. Still glowing, this is quickly stamped into a valve head to be finished by grinding. In this way, 180 valves an hour are produced from one machine. The rough camshaft forging is turned on a special lathe. Controlled by master cams, 9 cutters operate at once to form the correct profiles on the shaft. For grinding, the cut is controlled by moving the camshaft towards or away from the grinding wheel. All the components of the power unit are produced with equal care and verified by expert inspection. The lift of the cams is scrupulously checked. Every piston ring is inspected for circularity by rotating it in a special gauge in front of a band of light, which is completely obscured throughout the revolution if the ring is true. The diameter and gap of every piston ring is measured by pushing it up a tapered bore until the gap closes. The distance it has moved then indicates its size. The oil pump, when assembled, is tested for performance on a machine capable of operating 16 pumps at a time. It verifies that each pump can deliver fully the pressure required. Tappets are checked for hardness, an indentation by a diamond point being recorded as a hardness reading on a dial. The pistons must equal the cylinder bores for accuracy, so they also are gauged on the pneumatic micrometer. Then they are weighed and selected in sets so that balance is still further assured. The connecting rod and piston assemblies are checked for alignment. Nothing must be left to chance if power in plenty is to be achieved. Now the separate components have to be marshaled together. They come on conveyors which connect up all the production lines so that there is no delay between production and assembling. On the assembling track, the cylinder block is equipped with its valves, valve springs, and then the camshaft. Into the inverted casting goes the crankshaft to be followed by the connecting rods, for power depends upon sturdy limbs. When the oil pipes and pump are in place, the oil tray and reservoir enclose the crankcase. With the engine upright, the gasket and cylinder head are soon fitted. Water branches, manifolds, and all the remaining parts follow, and at last a complete engine is ready for your car. More power has been created, and this newly found vitality is measured in the engine test. There we find that from one small engine comes power in plenty, no less than 25 brake horsepower at 4,000 revolutions per minute, to give you speedy travel as you take to the road and drive so carefree in your lively and dependable Austin car.